What up, guys? It's Hale. Today for Fractals, man, we're going to be checking out this swirly one. Whoa. Hey, your time slot ended an hour ago, and you're using our topic for the day. We were supposed to do the Julia set fractal.
The what?
That.
Oh, the swirly one.
But actually, fractals are just a series of self-similar repeating shapes.
Yeah, the swirly ones.
In fact, a fractal isn't even necessarily swirly. Early fractals were geometric and created by hand, such as the Sierpinski's triangle, which is drawn out here. You start with an equilateral triangle, then divide each of its sides in half. Now connect the halves, forming another triangle between the lines. Now, this essentially creates three self-similar shapes.
That's a triangle.
But that's not true. To create a true fractal, this process would actually be repeated infinite.
Hate to be Captain Obvious here, but wouldn't that take a while?
In theory, yes. So, why is this a fractal and not just a shape? Well, the answer is in its dimensions.
To understand this concept, let's look at a shape we're all familiar with, the square. Now, for the triangle. We will also have two divisions on each side. However, this results in three self-similar shapes. So, log of 3 over log of 2 plugged into a calculator will give you a value of approximately 1.58.
Still, that's not like any fractal we've ever shown.
We're getting to it. Trust me. But first, another fractal to consider. This is the Koch snowflake, and this is also a triangle-based geometric fractal. And here we have an interesting paradox. The area of the Koch snowflake is obviously a finite amount of space. However, the perimeter is infinite.
I made a bird.
And you say my fractals aren't fractally enough?
But wait, it has fractal dimensions. Because if you cut it in half and divide the sides, you get a chicken sandwich.
Okay, so now why don't we take a look at the Julia set fractal that our friends at Fractals Man has set up. What? I'm not going to say it. Man. Ready? Our Julia set fractal is a part of a new generation of fractals generated by computers using a series of complex chaotic equations.
You just described all of high school. Complex, chaotic.
No, not like that. Complex means containing a real and imaginary number, 2 plus 3i. And chaotic describes the fact that these equations are nonlinear and extremely sensitive to input. This fact was actually discovered by our mathematician Edward Lorenz, who attempted to describe weather patterns with a series of differential equations. Edward Lorenz entered these equations into his computer. All of a sudden, our 90-degree beach day is below freezing. Eventually, Lorenz scrapped his equations for predicting weather, saying that while the present does predict the future, the approximate present does not approximately predict the future. This is tied into the chaos theory or butterfly effect, stating that when a butterfly eats an enchilada in South America and breaks wind, this could potentially cause a tornado in Africa. While the chaos or butterfly effect in ecology is dubious, the effects are clearly seen in mathematics, especially with fractals. The Julia set fractal is no exception. Hale, you still with us? We're doing the pretty one now. So, we can see the general shape by making a few simple calculations by hand.
The Julia set fractal is defined by a simple complex equation. Y equals z squared plus c. Now, it's not quite as simple as it looks because z and c both represent complex numbers. To begin, let's declare our numbers. We'll say z equals 3 plus 3i. And c, our constant value, equals 4 plus 2i. Using values I have pre-calculated, our first number comes out to 4 plus 20i. This number becomes the new z value. However, we can use the positive and negative values to graph an approximation of the shape that is formed by these numbers. Forming a series of ever-increasing swirling points as formed by the pattern of positive and negative numbers. Now, this is a very simple Julia set, and the more complex sets, such as those on our fractals board, involve many transformations of the same equation.
So, what good are fractals? Well, fractals are good for creating some very beautiful artwork, and it is this very artwork that keeps people, such as those at Fractals Man, off of the street and from operating motor vehicles. I don't know about you, but that's enough for me.
Whoa, is that a butterfly made out of magic?